So, good morning, everyone. Nice to see so many of you here, despite the early talk. So I'm going to talk a bit about Lego trains, a bit about REST, and a bit about actors, but it's mostly about having a bit of fun. So yeah, can have an easy start to the day. My name is Johan Janssen. I don't work for Lego, unfortunately. However, my boss allowed me to spend some of the time working on this during working hours, and he financed the hardware, so I'm pretty glad with that. You can reach me on Twitter if you have any remaining questions after the talk. I heard you need a disclaimer, so I always put a disclaimer on it. So no Lego was harmed, but a few Raspberry Pis died in the process. But I mean, who cares anyway? There are more than enough of them. This is a bit of the content. If you have any questions in between, please feel free to interrupt me, and I'll try and answer the questions directly. But first, you might wonder, okay, why is this guy playing with Lego? One of the good reasons, of course, is because it's fun. But it's also something we started with because we wanted to investigate a bit in the IoT world. IoT is really hip, as you probably know. But most of the time, people who develop software for IoT hardware, like a Raspberry Pi, they develop it in C or Python or some other lower-level language. And our company builds server applications with Java or Scala or other languages. So what we wanted to try out was if we could use the same languages and tools that we normally use to build large enterprise applications to build software for IoT devices, because that would be a lot easier for us to go in the IoT business. And it's also something that, of course, kids like it, so you can get kids excited for programming and a bit of hardware. And one of the things that I learned during the process is that it is also helping to explain certain concepts. If I try to explain to my wife what event-driven architecture is, and I tell her that it's sending message M from system X to system Y, she probably would have stopped listening at event-driven. And that's not really her fault. I mean, she doesn't have the technical background that we have, and we speak some alien dialect that nobody understands. But if I talk to her and I say, okay, I've got a train here, and if I send a message to the train, then music will start playing, then she can perfectly understand it, and I'm saying the same stuff. So it's also easy to explain certain concepts. If you're excited by this, be a bit careful, because before you know it, your living room will look like this. It was even a lot worse. I had this set up 3 times in my living room at once, so be careful with that. Yeah, it's work, yeah. So, I'm always, if I see cool talks, I'm like, okay, but how do I get started with it? How can I do this myself? And actually, it's quite easy. I made a list of ingredients that you need at minimum. First, a question to you all. Who already has a Raspberry Pi? Okay, keep your hands in the air if it's collecting dust on a shelf. Okay, so now you know what you can do with it. So without a Raspberry Pi, it's about 50 euros. If you already have a Raspberry Pi, it's like half the price. So you buy a Raspberry Pi, you buy a Wi-Fi dongle, a USB Wi-Fi dongle, a battery pack, and an infrared transmitter. And why you need that, I will explain in the next slides. But you can do a lot more with it. What you see here is a USB, or not a USB, a Raspberry Pi camera which streams Full HD video. There is a speaker on top of it, and there's an RFID reader at the bottom to detect the position on the track. Okay, so when I started using the Raspberry Pi A+, basically because it's a smaller Raspberry Pi and consumes less power, so I can run the train longer on a battery pack. By that time, the Raspberry Pi Zero wasn't yet available. If I would start again now, I would probably use the Raspberry Pi Zero because it's even smaller. And it even has a bit more memory than the A+ model. If you have other things like cameras or other stuff that doesn't have to be small and is attached to a power outlet, I recommend getting a faster Raspberry Pi, maybe the Raspberry Pi 3 or something like that, because working with that is a lot faster. If you install packages and stuff like that, it goes a lot smoother than either the A+ or the Zero, because those are single cores. And I also played a bit with the particle photon, which I will explain about in a minute as well. So a little bit about the architecture. I don't know if any one of you ever bought Lego, but you need to buy it in boxes like this, which is really annoying because you have to stack in the bricks at a good way so you can get most value from your money. And I'm Dutch and we're cheap, so I put everything in it what was possible. I don't know where I need the green ones for, but I mean, I paid for it, so I put them in. So about the applications, LTCC stands for the Lego Train Control Center. You always need a good abbreviation. Front end, we built it in Angular. The back end, we built it in Java. I thought this was the official REST symbol, but that doesn't really appear to be the case. So there's a REST interface here for the Angular application, and from the LTCC application on my laptop, I connect to the device control application on my Raspberry Pi, and the switch control application, which is also on my Raspberry Pi. So those are basically the applications that I have running. It's all with Java, all with REST endpoints, and underwater we use some C and Python libraries because they were already available and we could tweak them a little bit, and then it worked, and we didn't have to build it ourselves. And you see on here I have an application for the streaming of my video, which I will show you later as well. So that was already cool, but we had a Scala and Akka course, and we really liked Akka, but we wanted to do something with it and not build Hello World, but something cooler. So we thought, okay, let's rebuild everything with Scala and Akka. So the biggest change here is that we still have a REST endpoint for the Angular application, but from my laptop application to the application on my Raspberry Pi, both Raspberry Pis, we're using remote actors instead of REST. And that worked a lot nicer according to us. And we still needed one REST endpoint because the RFID application uses a REST endpoint as well. So that's a bit about how the applications are working. From a hardware perspective, we started working with a router, simply attached all the Raspberry Pis, laptop, and everything through wireless 2.4 gigahertz. Worked beautifully at home and at work. But then we tried to demo it at a conference where there were like 100 Wi-Fi hotspots and basically everything crashed. So then we thought, okay, how can we fix this? And it was quite easy. We basically wired most of the stuff, except for the trains, because that would look rather silly if you have a cable running after your train. So from the router, we connect to the Raspberry Pi, to the USB Wi-Fi dongle, and then the Raspberry Pi has the infrared transmitter, which basically connects to the infrared receiver, which is from Lego. And with that, I can control the Lego. So originally, it looks like this: infrared receiver, infrared transmitter, infrared receiver, battery box, and some engines underneath. The receiver is quite nice. However, it's infrared, so you only have a reach for a few meters. When I tried it out in my apartment, when I tried to drive from the living room to the kitchen, I couldn't even control it anymore, and it crashed full on into my kitchen doors. So it's not really useful. So I tried to find a solution for that, and that's basically using infrared attached to the Raspberry Pi. So this way, I can control my trains as long as they are within Wi-Fi range. And I can control as many as I want. With the normal infrared transmitter, I can only control 8 trains. With this, I can control as much trains as my Wi-Fi will allow. So this is everything you need to get going. Except for the USB battery pack, of course, because else it won't start. And the fun thing is, I didn't have to fiddle with the Lego engines. I could simply just send the infrared commands like the original infrared transmitter did. Sound, of course you need sound on a train to make train sounds, but it's also really useful to scare burglars away or your kids or partner. I use RFID cards. So the ones you see here at the bottom and over there, basically to detect the position of the train on the track. Next to that, I use the camera. For cameras on the Raspberry Pi, I found out that it was quite difficult to get good video streaming. Most solutions have a delay of a few seconds, and with a few, it's more like 5 to 10 seconds, or it only works in an application like VLC. The delay wasn't really useful for me because within 5 seconds the train would be across the track a second time, and I didn't want to use a solution like VLC because I wanted to integrate it within my application. Luckily, I came across this application, the RPI Cam Control, which I can highly recommend if you do anything with video streaming on a Raspberry Pi. What this one does is it's basically taking pictures. So you refresh pictures really quickly. And I cannot notice that it's not a video. It's refreshing every few milliseconds. And it has almost no delay. So it works perfectly. If you're a bit older, like me, you maybe had the older Lego trains. They had automated track switches. You could simply press a button, and the track switch would switch. The new ones, they don't have it. They simply have a yellow lever that you have to push yourself. So that's a bit uncomfortable. I mean, I don't want to walk there and pull the lever. So we decided, okay, we'll also automate it. And we first looked for some solutions, and I saw some people using Mindstorms, but that's really expensive. And I saw some other people who basically, they drilled some parts of the Lego to make the switches move easier. But if you intend on doing that, don't tell that on a Lego forum. They will hate you forever if you mess with the Lego. So I looked a bit further for another solution, and I found this. This is basically servos controlled by a Raspberry Pi servo board. And you need a bit of power with a laptop adapter or some other adapter. And then you can simply pull the levers up and down. However, it was quite a costly solution because these paper clips, they need to be the exact length because either it won't close or open. So we spent half a day with 4 colleagues bending paper clips. Was a bit annoying. So after all the trains were working, I was like, okay, this Ferris wheel, this is also really cool. Maybe we can integrate that as well. So I looked how I could integrate it, and actually it was really easy because here you see the same infrared receiver. Let's see where it's over there. Infrared receiver that's used on the train. So basically the only difference is that they use another engine. The engine you can see over here and let's see, over there. So Lego has a few different engines, but the infrared receiver is the same. So I could deploy the same application on my train and on the Raspberry Pi for my Ferris wheel. So that was really easy. So every IoT project needs to do something with LEDs. So I was like, okay, how can I integrate LEDs? And I thought it would be a bit silly to use a Raspberry Pi for that because that's overkill. So I looked a bit on the internet for other cool solutions, cool hardware solutions, and I found these particle photon boards who are really small. You can see one laying over there at the front of the table. But they work really well. They have Wi-Fi on board. It's Arduino-like, so you program Arduino code. But the cool thing is, it has a complete cloud environment. And so when you buy a particle photon, you connect to it with your smartphone, you enter your router credentials, and then it automatically connects to the cloud environment, and you have an IDE in the cloud where you can program it, and then simply flash the particle photon that you have. So I really like this solution, and it is a fairly cheap board, so it's a nice solution. The cool thing is that this cloud environment is now also open to Raspberry Pis and other devices, so it's becoming more of a general cloud environment. So let's do a little demo, because probably you're already waiting for that for a long time. Oh, my camera went a bit down. So there's one camera which I just used, which is basically wired. The camera on my train, I disabled it for now to make sure that I didn't have any Wi-Fi issues. I can simply control the trains at different speeds. If you look at the LEDs, you see there are 3 LEDs, or 3 LEDs at the front. They display the speed of the trains. And they go back or forth depending whether the trains are moving back or forward. For the blue train, we see that here it will show the position of the train on the track. Hopefully it will read it. Yes, so the train is now at cow. It will now move up to the bicycle, the crossing. So basically we can do position detection with that. Let's make sure it is over here. And I can play any train sounds that I want. So that's, of course, you need that when you build a train. But, I mean, you can play any noise with it that you want. So if you... quite useful if you want to scare someone away. But that's all manual control. And I was like, okay, how can I make this a bit cooler, not only do manual control? So I also implemented a bit of autopilot. And to give an example, I mean, I can just, these commands are sent to the Lego train one by one, or not one by one, they're sent at once, and then the train will execute them one by one. So I can shut off my computer in between, and the train will just continue executing this. So what this will do is, it will move the train at speed 3 for 3 seconds, then it will stop for 3 seconds and play a song. So let's see if it works. Okay, so that's just simply sending commands. Still, it's just one train doing one thing. But it can also do location-based commands. And what that means is I can specify a location and a speed. And then when the blue train reaches the bicycle, the white train will start moving at speed -3, etc. So let's open a second one. So now the trains basically react on each other, and I could even implement it in a way that if the blue train would reach the bicycle, that it would reverse or any other thing that I would want to do. So they're now responding on each other, basically. Here, these are for the switches, but I didn't bring them because they're quite brittle and often don't work. So it's a lot of work to set them up with all the wiring and the paper clips and everything. And I already had a box full of electronics and was picked up by customs in Amsterdam. So I didn't want to bring any more stuff with me. Okay, so that was a short demo. So now I'm going to explain a little bit on how it's working with the actor system with Akka underwater. So who of you already worked with actors in Akka? Okay, a few already, okay. So actors are really simple to get started with. What you do is you simply extend the actor class and you define a receive method, and then you can say what to do when a message is received. This example is really simple. It will simply print the message that's being received. Then in another class, we can define an actor system. And then the next step is that we ask the actor system to give us a reference to the worker actor, which is the actor that we see at the top of the slide. When we have the reference to the actor system, we can send it a message. In this case, I simply send a string to it. Normally, you would probably use case classes to send messages to it. But that's everything that you need to do. The nice thing is, this is for sending messages within one JVM on one machine. But you can also send messages across JVMs. If they're running on the same machine, that's okay, but also if they're running on multiple machines. So I have actors running on my laptop, and I have actors running on my Raspberry Pi. Normally, within the REST world or SOAP world, I would need to define endpoints and then connect to that. It's not the case for remote actors. They're a lot easier to work with. Because if we want to have a reference to a remote actor, we can simply say, okay, get me the actor, and specify the name of the actor system, the IP address, port, and the name of the actor. I put it here all in the code, but you could also put this in a configuration file. That would have been nicer, but I wanted to have a simple example which I could show on one slide. So that's everything you need to connect to a remote system. And especially nowadays, when people are talking about monoliths versus microservices, some people say, okay, we start with a monolith, and then if it grows too big or we want to extract parts of it, we do that. But if you do that with REST, you need to define all kinds of REST endpoints, connect to those REST endpoints, and that's basically all boilerplate code. With Akka, you don't need to do that. You simply call those actors and just provide a little bit of extra configuration. And this is a little bit of configuration you need, but that's basically copy-pasting. Maybe you want to change the port or the host name, but the rest is simply standard stuff. One thing to keep in mind is when we send these messages back and forth, of course, those messages, the message type needs to be understood by both parts, both by my laptop and the Raspberry Pi application. So I sent these messages from one JVM to the other JVM. For instance, the play message. So what I could do is I could define the play message in both applications and basically make duplicate code for it. That's one solution. The other solution is to create a library where we put in all the messages that we want to send back and forth and use that library in both applications, just like this. So here we see basically two messages. One is a play message, and we specify the name of the file we want to play. And the other one is a music list, which returns a list of files that are located on the Raspberry Pi on the train. So that's basically all you need to do. And then you can say, OK, use the package where the music service message is located in and send the play message. That's everything. So we really liked Akka, but we wanted to make like an overview of why you would use remote actors instead of HTTP. So for me, the biggest advantage of remote actors was that it feels more natural. You don't have to write all kinds of those boilerplate codes for HTTP endpoints and stuff like that. So that's really easy. It's all handled by the framework. But of course, the advantage of HTTP is that it's independent of technology. So I can call an HTTP endpoint in a C# application from a Java application and vice versa. In an Akka application, you cannot do that. You cannot communicate between an Akka.NET application and an Akka application running on Java because it's using the serialization mechanisms of those languages. So if you want to communicate between different systems, you still need to use HTTP. It's possible because Akka also supports HTTP, but then of course you lose part of the benefits. And one other advantage of Akka is that it's not using the HTTP network layer, it's using Akka over TCP, so it's on a bit lower network layer. So we really liked it, but we wanted to try and convince people to use this. And we were like, OK, how can we give some hard figures instead of just say that we like it, because maybe some people won't believe it. So at first I looked at the applications, including all the dependencies or the fat jars, to see if there was a big difference. And here you can see that remote actors are relatively small in size, but still quite comparable to Spring Boot. So it's not really a clear win. Then we started doing some performance tests with Gatling. Anybody of you already used Gatling? OK. So Gatling basically has a Scala DSL and is really easy to use. I've used JMeter in the past, but I like Gatling a lot better. It's really easy to get started with. It's even that easy that I can show it on one slide. So what's happening here? We create a scenario, and we say that it has to be repeated 100 times. So basically, it's a loop that will be executed 100 times. Within that loop, I will do a GET request to the ping endpoint and check if the status is 200, or basically an OK. After each ping, I will do a pause for a few milliseconds. That's the loop. And at the bottom, we can see that we ramp up 1,000 users over 10 seconds. So after 5 seconds, we will have around 500 users. And we changed the number of users, so we did a few different tests with it. So this is everything you need to do a performance test with Gatling. So what did we test? The part on the left is the same for the test at the top and at the bottom. So we simply connect from Gatling to an Akka HTTP endpoint running in a JVM. The difference is in the right part. At the top, we connect to another Akka HTTP endpoint, and at the bottom, we connect it to a remote actor. So basically, we use this to see if there is a difference in speed when connecting to a remote actor or Akka HTTP endpoint. And these are the mean response times in milliseconds for 50, 500, and 1,000 users. So here you see, especially at the right, with 1,000 users, remote actors clearly win. The same goes for the max response times. There are also clear winners with remote actors. I also had a graduation student who did a comparable test to this one, and he tried to figure out how many users he could handle. And he found out that with one system, with a REST application, he could handle around 600 users, and with remote actors, he estimated that he could handle 3,300 users. So from a business point of view, this is the difference between buying either one server or buying 5 servers, basically. So it can make you a lot of money. And so it's easy, you would say. But I was like, OK, so this is comparing all kinds of Akka stuff. It's all fairly new. Let's see if we can compare it with something that is a bit longer in the business and a bit more common, like Spring Boot. For whatever reasons, my colleague didn't get this picture, but you're all smarter, so. So here I compare remote actors with Spring Boot, and it was a bit unfortunate because Spring Boot was winning. So I thought, okay, what to do next? I mean, I can falsify the results because I mean, never trust statistics that you didn't falsify yourself. Because this was a bit of pity, like, okay, what am I going to do with this? But then I noticed that in the max response times, here you can see that the blue one, the remote actors, with 1,000 users, was performing a lot better than the green one. And that's because Spring Boot was consuming almost every CPU cycle, and remote actors were still able to scale a bit further. I have to make a note with this. I didn't do any performance tuning, except for the REST template in Spring, because the REST template in Spring uses a connection factory that isn't really capable of handling high loads. After around 300 users, it basically crashed. So instead of that, I used the connection factory from Apache to make sure that it could handle 1,000 users. But that was the only change I made to the application. So here we can see that if you have highly concurrent systems with lots of users, then I think Akka actors are a really good solution. They can handle the load really well. So a little bit about the challenges that I had. This isn't my house, because probably I would have been insured very well anyway, so that's not a problem. But I burned down some of the infrared transmitters. I bought some from China, then I looked on the internet on how to connect them, connected them, grabbed a coffee, came back, and it was smelling a bit in my room, and they were really hot, and that was basically the end of my infrared transmitter. Luckily, most of the stuff is really cheap, but it's all from abroad, so just simply order a few extra ones if you start playing with it, so you have a few spare ones. So I reached a bit of the limits. As you saw in an earlier slide, the Raspberry Pi A+ has 256 megabytes of memory. Running Java or Scala and some other applications on it reached the limits, basically, of the Raspberry Pi. But if you would use the Raspberry Pi Zero, you already have double the amount of memory, so you can do even more with that. So it's quite okay from a resource perspective. One thing to keep in mind is if you start using the Raspberry Pi A+, be really careful with the USB connector. I bought 3 of them, tried the first one, didn't work, tried the second one, didn't work, tried the third one, it was working. And then, like I did with the first 2 ones, I inserted the USB Wi-Fi dongle and it stopped working. I took out the USB Wi-Fi dongle and I noticed that the pins, which you can see over here and over there, normally they keep the connector like this. But now they were bent backwards like this and basically short-circuited my Raspberry Pi, which was the end of my Raspberry Pi. There is a really simple solution for that. Just use a screwdriver and push the pins a bit up, and then you can easily insert your USB device. Another thing I didn't really like, I really love Lego, but the trains are really picky about batteries. So using rechargeable batteries sometimes works, sometimes doesn't work, even if you have a good brand. So I needed to use non-rechargeable batteries in the end, which is a bit unfortunate. Using RFID, I use RFID for position detection. It works as long as the trains don't drive too quickly, because the RFID card and reader need to be quite close to each other, and you need to move over a bit slowly. But there are more advanced readers for RFID available, but they cost more money. This solution costs like $5 or something like that, so it's a cheap solution and good enough for my application. Wi-Fi, like I told you, I had some Wi-Fi issues, so I thought, okay, let's simply switch to 5 gigahertz. But 5 gigahertz USB Wi-Fi dongles are really poor supported on Raspberry Pi. I don't know why. But luckily, nowadays, everybody switches to 5 gigahertz, and I'm still on 2.4 gigahertz, so the problem solved itself. In the end, it wasn't really plug and play. You have lots of options. So when I started with it, I wanted to run Docker on the trains, not because it helps anything, but I really like Docker and would love to use it. So I had Docker running on Arch Linux on a Raspberry Pi, worked beautifully. But all the software I was using for the RFID and everything, it had support for Raspbian and not for Arch Linux. But Raspbian had poor support for Docker. You had to cross-compile Docker on another machine and a lot of other stuff. So in the end, I opted to just not use Docker. Luckily, nowadays, Raspbian also supports Docker, so you can use it if you want. There's lots of documentation, but be careful, not all the documentation is right. So if you burn something, it's just a pity. Kits with Lego, it's beautiful, but be careful if your kits are too small, like my kits, then you need to clean it up quickly before they enter the room. But the biggest challenge basically was time. I often get the question like, how many time did you spend on it? And I don't know it because it was lots of evening hours, sometimes during the day. But even if I would know it, I probably wouldn't tell you because my wife would be really upset if she would know how many times I played with Lego. Sorry, I worked with Lego. So this is a nice demo, and maybe you want to get started. You know already what hardware you need to buy, but how can you get the software up and running? The software we are using is a bit complicated and written in a rush, so we didn't really want to open source it. But what I did is I rewrote the basic parts, so to control everything in a Spring Boot application, the LCC application, and I made a script. And what the script does, it basically uses a Raspbian image, or you have to install Raspbian on a Raspberry Pi, run the script, and then it will install all the modules, set up the kernel, and everything that is necessary to get started. And then you can run the LCC application, which will expose a REST endpoint. And we'll show you how that works. So for that, I have this little truck, which basically uses already a Raspberry Pi 0, so not the A+. Also with the infrared transmitter, so it's the same basically as the train. It also has the camera on the back. Let's see if I can show the camera. It's hidden somewhere. Yeah, so there are you. Yeah, I see some people waving. It's working. Let's see if we can also make it moving. I just put it down here. I had a colleague of mine trying to do it on a table and then crashed, so it's probably safer to do it like this. I created a really simple REST endpoint with a few calls to make it work, but you can make a fancy GUI for it if you want. So now it's moving. I cannot even see it, but it's moving. So basically with this, I can control it and drive around whatever I want. And the fun thing is, I mean, you now saw that I did it with trains and with a truck, but you can basically control any Lego with it that you want. Let's try to make it move this way. So if you want to play with Lego and do a bit of programming, this is a nice solution. Also because it's a really simple solution. Let's see where I have it. So it's simply a Spring Boot application. I have a request mapping, which basically you can say what the intensity is, or the speed in this case, but you could also use it to control Lego LEDs and then control how bright the LEDs are shining. And the value basically is the speed in this case. And that's being used to send it to this other class, which basically determines whether it's a positive speed or a negative speed or a stop. And then it will execute that, or it will call a C application, which will then use the infrared transmitter to send the correct signals to the train or the car or whatever device that you have. So this is everything that's in the application. The rest is already automatically installed with the installation script that I also provided in the GitHub repository. So, okay. Conclusion, I think we learned a lot. We learned that we could use Scala, Akka perfectly on a Raspberry Pi, Java as well. The lessons we learned with playing with Scala and Akka, we could later use that in projects where we also use Scala and Akka. So despite having a lot of fun, it was also really useful for the company. We learned a lot from it. I can highly recommend doing something like this if you want to try out new technology, new hardware, new software. It will keep you going. If you build Hello World, you stop after Hello World, and you didn't learn anything, because, I mean, every language and every tool will probably support Hello World, because otherwise it's really crappy. So build something more advanced and build something funny with it. It will keep you going, and it is something that's nice to show. And it will bring you to nice places, like Krakow and all kinds of other places. Kids loved it as well, so that was also a benefit. So we learned a lot from it. There was one best part. Let's show that. In the meantime, if you have any questions, feel free to already ask them. We're approaching the end of the presentation. Yeah, there was one part that I couldn't really automate, but luckily my wife wanted to help out. So thank her for that. I have to say, she only did this once, not the entire evening. You probably already noticed what's coming there. So what you didn't hear was that when the train reached the fridge, it actually asked to supply beer through the speaker. And I could control it with my smartphone. I later saw some videos on the internet where a guy even made like a tap, and it automatically tapped beer on his Lego train. So that was even cooler, but... Sorry? Oh, yes, of course, I can show them again. Is this one? No problem. So if you have any questions, you can ask them now, tweet me, email me, whatever you want. So any questions? Okay, then thank you all for joining and have a good conference.